Today we feature Donna Strickland, a world-renowned optical physicist widely recognized for her groundbreaking contributions to the field of pulsed lasers. In 2018, she was honored with the Nobel Prize in Physics for the practical implementation of chirped pulse amplification alongside her colleague, Gérard Mourou. Her brilliantly blazing research has left a lasting mark in many fields, and most notably it has significantly advanced laser eye surgery, something I benefited from myself many years ago, which has enabled doctors to help millions of people around the world. Donna fell in love with science early on, and as she grew up, so did her love of science. Today she'll share some of that love with us, so buckle up and get ready to peek into the fascinating mind of a Nobel laureate.
Welcome, everybody, to this episode of the Into the Impossible podcast. Today is a special segment, part of our series called Fake Like a Nobel Prize Winner. And that's because we have an actual honest-to-goodness Nobel Prize winner. The fourth one has been in this room, and the 17th one that's been on the podcast. So I'm just overjoyed with gratitude that Donna is here. We're going to talk about technology. We're going to nerd out as experimental physicists. But the first thing I really want to talk about is pedagogy. And sort of philosophically, how do you approach dealing with students? Have you seen changes in your attitude or perspective in teaching over the years? Have there been any technological improvements? I'm always looking to learn different tools to apply for my students, and curious about how you approach and divide your time, research, and pedagogy. So what is your philosophy as an educator, as a mentor to students?
Well, now I don't teach because I won the Nobel Prize and I'm traveling all the time. Before that, the only thing, I did follow physics education research, and the one thing I am doing for undergrad education right now is changing the labs. I am supposedly the director of undergrad labs, but since I won, they've hired someone to do the actual work. But it's still my vision. And really, because at Waterloo, we have this perimeter institute of theoretical physics. So many of our students come thinking the only kind of really cool physics is theory. So I'm trying to fight back on that and say, no, I think seeing things happen in front of your eyes, and optical physics is the best for that. One of the things I'm aiming for is to have a first-year gee-whiz lab just for the honor physics students, because I want the students from that program to leave that lab going, too bad for the rest of you. You don't get to see these labs. Because usually first-year undergrad labs leave everybody like, oh, I'd rather be a theorist, right? And so it's not going to be to teach them concepts, because physics education research has shown that the first-year labs, where we've done them for decades, doesn't do that. So instead, we'll still have a set of first-year labs to teach them skills and stuff. But this one, and the one I wanted to do, was white light generation. That requires too expensive of a laser, and possibly one where laser safety may be more of a concern. So we're just going to do, in my optics one, we're going to do frequency doubling and let the students just say, well, just think about the experiment yourself. You want to find out, is it image dependent, power dependent, intensity dependent, and that little pre-thing about what those differences are. But just let them figure out how to do the experiment and let them make observations. And of course, they probably won't come up with the right answer. And who cares? Nobody cares. It's the fact that they get to see it. They get to think like an experimentalist and go, well, what should I try here with the equipment that I have, with the scheme that we have? What can I try to figure out if it's power dependent, energy dependent, or intensity dependent? And just see the light just turning from infrared to blue is one thing, So that's just, it's a cool thing to see. So that's what I'm trying to do, is just get them excited about what is science, because I think the biggest mistake we make teaching all the way up through undergrad is we're always teaching what science we already know. And science is about not knowing, right? It's really about figuring out how to ask the question why or how properly. It's not about learning how everything else has already been done. I'm not saying we don't need to know that, but we don't really instruct asking, the right questions as opposed to knowing the answers.
Yeah, and oftentimes I feel like students get these canned experiments, and we already know that they're going to work, and they
don't work, and that's frustrating. And yes,
but that's when you learn, right? When this thing is supposed to actually do, and that's why I always find it so much fun when my theoretical colleagues come into the lab and they're stumbling about like they're toddlers in an NBA game trying to play against LeBron James or Toronto Raptors in your case, closer to you, but when you think about the kind of crown jewels, we were talking earlier before we started recording about, the paradigmatic Nobel Prize winners, the Einsteins, the Fermis. These are, Fermi has experimental capability as well, but the Dirac's and the, Gelmans and Feynman. And it's almost seen that the prestige in physics goes a lot to the theorist. And yet I find that a complete physicist should know, my philosophy is my grad students need to know as much theory as a theorist grad student, but they don't have to do new theories. What about like when you were teaching, when you were advising, what is the experimental minimum, or what do you wish theoretically inclined students like those at Perimeter, who are some of the best, that they knew about experiment? What should they know about experimental physics?
The limits. I mean, mostly it's the limitation, but also I think most people don't realize that how much patience an experimentalist needs. And the fact that the theorist gets to nonstop always think about their theory. At the end of the day, it doesn't stop. They pick it up exactly where they left it the next day. They might have to remind themselves a little bit. Whereas we turn our lasers off, we spend the majority of the time just getting the laser back to where it was the day before we can even start our experiment, right? And so there's a lot of that frustration that goes on. But also, I think that we actually get to see physics happening in front of our eyes. And to me, that's the most exciting part of it, is that we just get to see things happening.
When I think back and I have lowered spirits, maybe I think about Galileo, and he was just an amazing writer as well as a scientist, obviously. And he would say things like, measure what is measurable and make measurable what is not yet so. And I wonder, when you were, devising this new, heretofore unknown technique, was it done, with a teleological purpose in mind, that you wanted to solve a specific problem that would lead to, LASIK and all sorts of other things, or the technological breakthroughs that you've enabled, or your technology has enabled? Or was it just, playing around? Like, what was it? Was it driven from a fundamental, or with an ultimate goal of a technological application?
There was an actual goal to do a fundamental physics exploration. We were trying to do a high-order nonlinear optical experiment, whereas with regular lasers, they were able to simultaneously absorb the energy of 2 or 3 photons. We were going to try to jump to 9 photons. And so that was not going to require just a regular laser. It had to be an intense laser in order to have that photon density. And so we had the actual practical goal of needing the intense laser, but it was to just study how does light and matter interact when the intensity gets that high. That was, so we were not thinking how to cut glass. We were not thinking, this could be used for medicine. There was none of that at all. It was a fundamental pursuit of optics, but we needed the tool to do it.
So you had to invent the measurement tool to do something. Yeah, I would say when I have on, someone very high caliber, and I'm blessed to have on many guests of just great accomplishment. But I always say, I have to ask you about the actual Nobel Prize. I have to ask you. It would be like if I had Rush here, the rock band Rush, and I didn't ask them to play, Limelight. It's not a good skill for a podcaster to have to neglect a description from the creator of this. So can you explain, what is a chirp? What does this have to, what was the actual breakthrough discovery that ended up being that object of recognition that resulted in your Nobel Prize?
So first, the word chirp, we could have just called it stretched pulse amplification, because that's really what it is. But a bird's chirp is the fact that its audio frequency changes in time, which is, the sound you make, right? They're the notes they play. And it turns out that to stretch our pulse, we use dispersion. And we use it in a fiber. That's just that the red colors travel faster than the blue colors. So although they all start together, by the end, the red is out ahead of the blue, and that's a chirp. So we called it chirped pulse amplification. And the point is that, like I said, we were already in the range where you could have a second order or third order nonlinearity just with lasers. And this is what was stopping people from pushing the laser power even higher. When you tried to amplify a short pulse, it got too powerful. And the nonlinear interactions actually caused damage in the rods. Okay. And I like to say that for the experiment, what we were trying to build was a laser hammer. Because sometimes it's energy, which is the total number of photons, because each photon carries some energy. Laser fusion, which has just worked a year or so ago, finally, at least got scientific break even, is an energy in, gives an energy out. But like pushing a nail into a piece of wood, you can push with all you might, it doesn't go in, but you wrap it in and then it goes. So nonlinear optics is like that. It's the photon density, not the total number of photons. So when you put the short pulse in and got it amplified, it was just the density of photons so high, nonlinear optics happened and it caused damage to the rod. And so we couldn't do that. And so then we had to work around that. And it's a very simple workaround. You take your short pulse, you make it very long, bring the photon density. Then what the amplification does is just multiplies how many photons there are and gives total number of photons. But they're still stretched far apart. And then when you're safely out of the amplifier, you compress them all back together. So you have your photon density high for the experiment of the application, but you've not damaged your amplifier.
I didn't know. I see. Okay. And does the polarization state of the photons play any role whatsoever in it, or can it be done unpolarized, or is there dichroic or birefringent effects that are...
You can do it all of those ways. One of the few problems that we had when we were first developing it is we were the first people. A short pulse necessarily has all the colors, right? Because a single color has to go on forever, and then you start adding those colors, they cancel each other, and that's how you make a short pulse. So we were really one of the first to then even try to amplify a broadband color into these amplifiers, and we ended up finding out this oscillation through our colors. And that's because we were using polarization switches to switch the pulse in and out of the amplifier, and there's a thin plate, and that thin plate's an etalon, and that was causing the problem. So we had to work around that. We had to get the plate out of there, or we couldn't have made it work.
Hey there, fellow cosmic adventurers. It's me, your fearless guide through the wonders of the universe, Professor Brian Keating. As a passionate educator and science communicator, my mission is to make learning captivating and fun. You see, equipping students with the tools they need to unlock the mysteries of the universe is not just about rote memorization. It's about turning the entire process into an adventure, one they won't want to quit. And by making it into a thrilling journey, it'll be one filled with excitement and a touch of playfulness. And that's why I love Brilliant so much. Brilliant is an intuitive and hands-on platform that encourages you to approach STEM subjects like science, technology, engineering, and math the way a scientist like me does. With Brilliant, you don't just learn new things, you learn how to think. And that, in my humble opinion, is the key to education. It's really the best way to learn. Brilliant offers a wide variety of lessons in different STEM fields like mathematics and computer science. Their courses range from basic to advanced levels, and they arm you with new content from cutting-edge disciplines like cryptography and computer science. And you get that information every single month, increasing your learning adventures and taking a journey that's uniquely tailored to you. You can even unlock cosmic wonders from stellar life cycles to the fate of their universe in their astrophysics course, approved by yours truly. To try everything Brilliant has to offer for free for a full 30 days, visit brilliant.org/Dr. Brian Keating, Dr. Brian Keating, or click on the link in the description below. The first 200 of you will get 20% off Brilliant's annual premium subscription. Now back to the episode.
So we can get back to some of the technical details and nerd out maybe in a little bit in the remaining minutes that we have. But I want to talk about lasers. So lasers reportedly have been, as a category, have garnered the largest share of Nobel Prizes.
So that's good to know. I didn't know that. As they should, and they just did again.
That's right. So first of all, I wanted to get a comment on that. And then second of all, comment on, you were at Lawrence Berkeley National Laboratory.
Lawrence Livermore National.
LLNL, yeah, up north here in sunny California. And I want to get some thoughts on some of the projects that folks like Charlie Towns were working on, including communicating with aliens or looking for signals from short pulses of laser energy. First, could you please comment on this most recent Nobel Prize won by 3 physicists? Of course, just a few weeks ago, that was Agostini, Krauss, and Lhuillier. So how did you react to that? I always said you said it was a good choice.
I was very happy about it. I actually did my postdoc with Paul Corkum notes, so we kind of did think he might win if attoseconds won. But I mean, I don't want to take it away from the other 3 because they all deserve the Nobel Prize too. And so obviously we're happy when I am an ultrafast laser person, and that's the ultimate ultrafast right now is attoseconds. Also, most attosecond work is done with CPA lasers, and so it was our laser that helped push. It helped push it, but it's funny when I say that what I was trying to do for my PhD is 9th order harmonics. Anne Lhuillier saw the 33rd harmonic before I even got to it and blew my thesis right out. So she actually saw higher harmonics without CPA, but now it's yes. But it was done with more energy and longer pulses, and that would be done with less energy and shorter pulses. And I think she probably CPA to get up to the 90 or 100 and whatever harmonics and stuff. But yeah, we're all, the short pulse people know each other. And so it's always fun when your colleagues are the ones that win. and that your field is recognized.
So one thing, again, going back to Galileo, he was fascinated with time. As you know, he measured pendulums, and he tied his pulse to because there weren't clocks back then. So a question that often comes up: how do you know these pulses are added? I mean, what clock do you use? I had Bill Phillips from NIST on early this year, maybe late last year. And we talked about lattices and trapping and measurement of time and the standards and technology used for that. How do you know these pulses are really attosecond or, femtosecond? How do you actually?
Well, actually, this is why Pierre Agostini won his, is that he came up with this rabbit, and I'm not going to explain it, attoseconds. But I'll tell you the simpler one, because back in the femtosecond time, and these will be just fancier versions of the same, is that optical pulses are the shortest pulses that get to be created. So you can't just use a regular detector which uses electrons, because they move slower. They have mass. They simply move slower. And so we use some kind of, all of these things are some type of autocorrelation, which means that you really are taking one short pulse to measure another short pulse. And the correlation is really just if you take the one short pulse with the other, and what's the overlap, what's the overlap, what's the overlap, what's the overlap, and that's how you do it. And so as long as you have a short enough pulse, then of course we have this thing where space, because the speed of light, you can just delay with a delay arm and know exactly how much you're moving this by.
Hey there, fellow explorers of the impossible. It is I, your fearless host, Professor Brian Keating. How are you enjoying this riveting conversation with yet another Nobel Prize winner? She's the 17th on our show, but who's counting? Now, here's a little secret. You can help me help you by subscribing, liking, and leaving a review on either the audio podcast or on YouTube. These reviews and thumbs up and interactions, as they're called, give us a huge boost in different algorithms that seem to dictate our lives in all things that are related to creative content like this podcast. So by hitting the subscribe or follow button, giving us a thumbs up, and leaving a 5-star review where you can, you'll enable me to bring more of these incredible minds to the show. So please do that. Do it now before you forget. Now, back to the episode.
So fellow Canadian Katie Mack, who is now at Perimeter Institute, she's the Hawking chair there. I had her on many years ago, and I asked her about what can we do to increase the enrichment of women. And I'm father of many daughters, and I'm quite happy with that. She didn't want to talk about it. She felt like she gets asked it too much, and what do you want to do? What is she going to do? Propose you have a pink circuit board for the girls to use and a blue one for the boys. Speculations on kind of the role that how things have changed, what they need to change. And what I call the Nobel tax, which is that you're often asked probably to comment on it. What are your feelings on how status of women has changed over your career, and where do you see it go?
Well, it's changed, but I don't think that's the point. I think the point is that physics itself is not viewed by society highly. And so if you look at medicine, all these other issues that they will say this is why women don't want to do physics would have been true in medicine as well. And yet now more women go to medicine than men. And so if society, right, parents still tell children that are good on science become doctors, if they're good on the arts to become lawyers. Maybe now there's some computer science because there's so much money in that. That's right. And this is how society values things. It's with money. If you get paid really well, then society is really saying, we value this. Physics is not one of those valued things. So it's a rare thing. Doesn't matter if you're a man or a woman. And so this is where I sort of stand until society says this is something to do. I find it very strange to say, why don't women want to do it? Well, they just don't want to do it.
So overall, lift all boats, and there'll be some fraction of women that get involved. I've noticed many more women, just in my 20-year career here, that have gotten involved with it and excelled, and starting to worry, is there a pendulum effect? And I have to worry about my male students because, it's 60% of all college graduates are women. It's gone up to 70%.
At some point, we have to worry about it. And there's certain fields. I mean, we have a School of Optometry. It's the only English School of Optometry in Canada. And it's mostly women. And I never hear anybody say, wow, what happened? It used to be mostly men, and now it's mostly women. And when do we start asking, where are the men? Yeah. And that doesn't seem to be a concern, and yet the lack of women seems to be a big concern in physics. So I think we have to always be concerned about it, and I think the other real problem, and the problem in the 70s in my time, is that women were told we could do anything, but the men were told you also have to do your share. And this comes even back to, if you think about Maria Goeppert-Mayer, when she won her Nobel Prize, the newspaper here wrote, San Diego housewife wins a Nobel Prize. And that's because everybody had to say, it's okay that she's doing science because she's also doing all of her women's jobs too. Well, this is not possible. It's not possible for us to do twice as much, right? So you will have around the world gender equity when we also let men look after the children and the elderly. It bothered me during COVID that it was like, well, all the women have to lose their jobs because they're the ones who have to look after the kids or look after elderly. Why? I don't think women are more caring than men. I think that's just as offensive as saying that, you know, women aren't as smart as men, right? There's none of this, you know, if everything was equal and everybody took their share, then everybody, you know, could have an equal shot at it. And so this idea that, yes, men should even be allowed to work morning, noon, and night and that women will just look after it is wrong. Everybody has to take their share, or, you know, or you hire nannies and housekeepers and everything else. And so that's fine. It's a different way to go.
Last year on Twitter, I tweeted out the same tweet. I got the image from the Union Tribune, which is the San Diego newspaper that printed that headline. And I put it on my Twitter account, and I said, and I shared a screenshot from JPL when your co-laureate in chemistry, Frances Arnold, who's a friend of mine, and the widow of my postdoctoral advisor, Andrew Lanning at Caltech. And it said, JPL mom wins. Oh, no, it said Caltech mom wins Nobel Prize. Son is JPL flight tech. And it was the same thing. It's like completely defined. But then just 2 weeks ago, when I can't pronounce her name, Karolina, the Hungarian woman who won for mRNA, she won. She was like, yes, I'm a mother of a swimmer. So it the kind of attitudinal. And Frances took it all. She was like, well, they corrected it. Yeah. But, you know, you wonder, how much have things change and how much do we put, just men and women at a disadvantage by kind of antagonizing this relationship, which, as you said, should be a mutual thing. It shouldn't be. And now many of us, unsung, in not just that you're taking care of kids, is that at our age, I'm taking care of my parents.
Yes, exactly.
And we're kind of sandwiched in and we have way too much stuff going on. That brings up something. You've done some heroic videos that will get probably more than this one, unfortunately, views on YouTube with Wired magazine, I think it was, and millions of views explaining different ways. But I want to ask you more generally, do scientists have an obligation to communicate with lay people? Or should we have more, just specialization, people in their labs or in their, cubicles and chalkboard and so forth? What do you view as an obligation of a scientist to communicate his or her research to the public that pays their salary at some level?
Well, not everybody's meant to be a communicator, but I would like universities to start paying more attention and that makes sure that every area of physics, there's at least one person that gets coaching and gets the opportunity to go out and explain it. I think it's important. I've started, I'm co-director, but I was sort of the instigator for this new network on trust in science. And scientists have to have conversations with other people so that they understand the scientific process. I don't know that people have to know each area of science. I don't think that's really critical. I think they have to understand the scientific process. Why does things take so long? Why, so masking was one of these things that people started to get really frustrated about. And yet it was really a science experiment happening in front of them. And scientists would, they now tested this and found that, so this is why it has to change. And to a scientist, that made sense. But to other people, they don't know what they're doing. They don't know what they're doing. And so this is where I think we have to get out and start really just explaining the process, explaining the timescales, explaining all of these things. There are certain areas of science and in physics and astro that you can usually get people out for public talks. But along with that, my daughter's in astrophysics, she's already given a couple of public talks as a graduate student. Yeah. So they also, because the public is willing to come, they also get the experience of learning how to give public talks. And most science students do not get that training. So I think the university has to start having better communication teams, working with the scientists, and giving us also more opportunities to get out there. But certainly Perimeter Institute in Waterloo transformed it. I mean, it was hard to get a seat at their Wednesday talks once a month, right? They brought in fabulous speakers and they just sold out right away. So there is an appetite for it and we have to tap into it.
Mm-hmm. Absolutely. Okay, well, we've reached the end of the scheduled questions that I had, except for these final 4 existential questions. You're free not to answer them. You're free to answer as long or short as
you like. Me about my name.
No, I want to ask you first about your name. Yes, indeed. Donna Theo Strickland. So tell me about Theo. Is there any relationship, theology, theodicy, theodolite?
No. My older sister was named Anne after my mother's mother.
Okay.
And my father's mother's name was Theodosia. Oh. And so my mother said, there's no way I'm giving my daughter named Theodosia. But so she said, I'll put it in the middle name and we're going to cut it to Theo. And that's where it comes from. But really, I mean, I used to not use the middle name much. Most people don't use the middle name, right? But now it's sort of a different kind of name. Very few women, some men go by it from Theodore.
Yeah.
And so, so why don't I even use it? Most people have the two initials on their papers. But my very first paper, I was very interested in making sure that they understood that I was a woman, because it was rare to be a woman in the laser business. And so the paper was at Optics Communications, and it let you put your full name. So I just wrote Donna Strickland. And I didn't, so that was long enough. I didn't need the Theo. And then, so all of my papers from my grad time is just D. Strickland. And then I go to work with Paul Corkum, and I see that he's PB Corkum. And I go, well, if you're PB Corkum, I should be DT Strickland. So I switch, which of course is wrong, because now to find somebody, you have to pick one. And I didn't really catch on to that. And then it's funny, I go to Livermore, and I work with this brand new grad student, Todd Dittmeyer, who's now a well-known professor at Texas Austin. But he said, no, I don't want, our first paper together, he goes, I don't want to publish with DT Strickland. I want to publish with D. Strickland. That's what I want to publish with. And I let this grad student convince me, all right, let's go back. So from then on, I've always just been D. Strickland.
Oh, I think things worked out, so for the best. So the first thing I do is hearken to the Nobel Prize itself. So part of what Alfred Nobel did, as you know, probably better than anybody, and me certainly, was that he wanted to do kind of imbue the Nobel Prize with a social aim. And that was to improve for the betterment of all mankind. So in Judaism, we have this concept of something called an ethical will, which is not monetary, not what you're going to do with your fraction of the Nobel Prize winning, the gold medal, but what wisdom or knowledge that you most want to transmit to your biological, but also your ideological heirs, of which there's many.
I think that, and this has come up in this study where the Stanford professor and some other professors looked at the fact that our research productivity goes down. I think the one thing that once you win the Nobel Prize, I think because people listen to us and they don't listen to other scientists, the onus is on us to start talking about the importance of science. I think I'm a big believer that it's an economic driver, obviously can help things with medicine and all these other things. I also think it's important for people to understand that you can be working on something like studying nuclear magnetic resonance and not realizing that it's going to end up being a magnetic resonance imaging machine in a hospital 50 years later, right? And so you have to let scientists have that time and that, just area to explore whatever they want to explore, because you don't know what's going to leak down there. So I think that's the one thing I would say is that we do have to get out there and play our role as ambassadors for science.
Very good. The next question. So this podcast originated as part of the Arthur C. Clarke Center for Human Imagination, which I'm associate director of here at UCSD. And I like to address the next final three questions to different aspects of his career, but we'll tailor it to your take on it. So one, have you seen the movie 2001, A Space Odyssey?
No, because I don't like science fiction.
You don't like science fiction. Okay. Well, there is, I'll phrase it in the form of Richard Feynman. So Richard Feynman was once asked, what is the shortest sentence that contains the densest amount of information that human beings have learned about the universe? And I usually say, what kind of thing would you put on a time capsule that would last 1 billion years? What do you think is the most impressive aspect? As Arthur C. Clarke said, any sufficiently advanced technology is indistinguishable from magic. So what is the most magical form of technology? You're allowed to say, but it's up to you. What is the most...
Oh, I was going to say, I thought it was an expression, because I think F equals MA is still the strongest thing. It's just such a small equation and just has been used for all these hundreds of years. F equals MA. Newton got that one right, and can't be beat.
Can't beat. Yeah, Feynman had the what he called the atomic hypothesis, that everything is made of these little atoms that are continually whirling around electrons around the nucleus. So then the next question has to do with advice to a younger Donna, and it goes like this. The name of this podcast is Into the Impossible, and the statement that Arthur C. Clarke made was the only way to determine the limits of the possible is to go beyond them, into the impossible. So I want to ask you, what aspect of life mystified you that if you got to spend 30 seconds with a 20-year-old Donna Strickland, what would you tell her, if anything?
No, I'm not that deep a thinker. I just keep going and just keep walking down my path. I don't think too deeply about it.
Is that because you wouldn't trade the experiences that you've had, and anything you do to the past will necessarily modify it?
You know, I've just been such an incredibly lucky human being through my whole life. You know, obviously I wouldn't really want to change it. Other people could look at it and go, you know, I was unbelievably shy as a kid, and that maybe held me back. On the other hand, it directed where I wanted to go, because I, at one point, decided that I would go to a university where I didn't know anybody to walk myself out of that. And that's what led me to go to lasers. So wasn't that lucky. To follow my husband, I took a job as a member of technical staff at Princeton, and I thought I was giving up the academic thing. I chose that time to have my 2 children, where I was quite sick through all the pregnancies. Couldn't have done it as an academic. So wasn't that lucky that somehow I just said, fine, I give up on my career. I got to have my 2 children, and then I still got back and had an academic career and 2 children. Who would have thought that was possible, but it was. And so I've just walked through life without a clear plan. And life just kept working out for me.
You, as my grandmother would say, dance between the raindrops. Well, I think Kierkegaard said that you can, life must be lived going forward, but it only makes sense when you look back. Okay, the final question, with your delightful forbearance, has to do with things that you maybe have changed your mind about. And it goes like this. Again, Arthur C. Clarke had all these quips. One was, for every expert, there's an equal and opposite expert. But his favorite thing in this way to wrap up this conversation is the following statement. He said, when an elderly, I'm not calling you elderly, but an elderly and distinguished scientist says something is possible, he or she is very likely to be correct. But when he or she says something is impossible, they are very likely to be wrong. And I want to ask you, what have you changed your mind about? What have you been wrong about? Do you agree with that sentiment?
I don't know that I would ever say anything's impossible. My husband kids me about how I always, used to say I would never do this, that, or everything. And I've gone, I told my husband I would never get married, but I did. I would never have children, but I did. So, I never, you don't know where life's taking you. So there's no point in putting limits on it. But I hope nothing's impossible. I still am waiting for something to be better than quantum mechanics. I think we will get there someday. I just don't know if it's going to be in my lifetime.
Fantastic. Donna Strickland, thank you so much for sharing so much of your time with us today, visiting us in San Diego, and I hope you have many happy returns here back to San Diego. Thank you.
Thank you.
Hey there. It's me, your beloved host, Professor Brian Keating. Are you enjoying my conversation with this newest Nobel Prize winner to be featured on the Into the Impossible podcast, Donna Strickland? Well, what if I told you there's more of the good stuff that you can have access to? And all you have to do to get it is go to my mailing list, which you can join at briankeating.com. By joining, you also enter a giveaway for a piece of 4 billion-year-old space dust. How cool is that? And if you have a .edu email address, you're guaranteed to win. So go to briankeating.com and you can enter in the pop-up splash screen that you'll see there. And I will see you in the next episode with my utmost thanks.